Assalamu alaikum. In our last lecture, we were at the topic of graphic posture analysis, which is about the posture, like the distance analysis for any mechanism. And we have briefly shown before we're doing the graphic posture analysis, different vector addition and subtraction method we have gone through already. And then it was established a mechanism, let's say a 4-bar mechanism, can be represented as sum of different vectors basically. And the terminology we are adopting by placing, so the bold letters actually they are the vectors. Vector notation for this book, so Theory of Machine by Shigley, and it has two symbols up there. So one of this symbol and one of this symbol. So the first symbol is basically is the state of its magnitude. So the first symbol, when it's shown as a good mark like that, is a magnitude, and the second symbol indicate its direction. So second symbol for each quantity is a vector. There is another way also writing this equation. For example, this one, which actually shows the vector and the magnitude independently. So the bold is a vector and the italic is the magnitude. All right, so then we have seen, it was discussed, because these two vectors are known. When we say known, means that their magnitude and direction is known, so you can literally replace them with one another vector, basically another vector. So for example, D and E were known, so they are replaced with A. So the final equation is like that basically, right? And based on this equation C and then 2.16, this table is being generated. So unknowns in a planar vector equations. So if you have like 4 vectors in a one plane, means 4 bar links kind of situation where you want to find out known and unknown. So in one case, let's say you got the magnitude and the angle, which is unknown. You can use the process to find out these unknown, and we can follow the procedure as described in figure, this one, and then equation. And the second, when you got A direct, so the vector magnitude of A and as well as the direction for B, vector B. And third case is A and B, so the both magnitude, and then we have the direction A and B. So in each case respective, we can use figure and a set of equation to find out the remaining unknowns. So we will do one by one for each case, and then we'll see. So the very first case, when we have C and theta C, which are unknown, so we can use equation, so basically equation 2.14 and figure 2.10. So this is the relevance here. So equation 2.14, which is this one, and then we have the figure 2.10. So in case 1, the two unknowns are magnitude and direction of the same vector. So C and theta C is basically direction and as well as magnitude of the same vector C. Say C and theta C. So the C is magnitude and theta C is the direction. This case can be solved by graphic addition or subtraction. So you have the option for both of the remaining two vectors which are completely defined. This case was illustrated in figure 2.10 here. So for example, you know the values for A and B. So when we say values, means you know its magnitude. Magnitude means the length, and we know the direction. For example, the angle is also known, and same goes for A. So A, we know the direction and magnitude. So then it's just matter of addition, which we have already discussed within the same presentation. So what is it basically? There are two options. One is you basically transfer this B vector over here. Just draw a parallel line to B, and then from head to tail method, which you would have done your elementary education. So this vector C would be A and B, sum of A and B, right? So similar way we got A is equal to, so the subtraction method can be used as well. Uh, yeah, so as it says over here, so you can use the subtraction method as well. So in case if let's say you have, A and B, so you can subtract from C to find out A basically. So it's the same equation basically. So it's the same equation but rearranged. All right. So then we have case 2 where we have A and theta B are unknown. So the two unknowns are magnitude and direction for different vector. So say A. So one case when we have the magnitude of A is unknown and the direction of B is unknown. So the vector equation is, so we follow this equation. So C is equal to A plus B. So you see within this equation, C is well defined. With A, you got unknown magnitude, direction known. And for B, we is the other way. So B, we have is magnitude known, direction is unknown. So the solution illustrated in figure 2.11 is obtained as follows. So this is the 2.11 as it says over here, figure 2.11, and then equation 2.17. So this equation. So the procedure we are following. So procedure is, first of all, the very first process is choose a convenient scale factor and draw C. So whatever the value of C is known, because in this vector, this value of C is known, its magnitude and as well as direction. So that's why we need a convenient scale factor for the length and draw vector C. Construct a line through the origin of C parallel to A. Now you construct a line. So in the direction of A. So for example, here we got C, which is definitely we know its length and its direction. For A, vector A, we have just the direction. So if you see, we just have the direction, we don't know the magnitude. That's why we draw a parallel line and longer line basically, because we don't know what is the magnitude of that. We know the direction, so we have done the parallel line showing the same direction, but we don't know the length, means the magnitude basically. Now what you do, adjust a compass. So basically it is shown over here. Yeah. So we got, this is C, this is C, this vector is C, and choose a line through the origin. So this is the origin. So this is the origin of C parallel to A, and you just draw the parallel line. It's going downward, the same vector. Yeah. So it's shown as A prime. It doesn't matter. So adjust a compass to the scaled magnitude B. Now, for B, we know the magnitude, right? So that's why we don't know the direction. So that's why we need to work out just the magnitude. So whatever scale you have used with the same scale, and now with the same magnitude, what you do, the scale magnitude B and construct a circular arc with the center at the terminus of P. So you draw a circle by placing your, like you do with the compass, for example. So one end of the compass over here, the second end with the length of B. So we don't know the direction of B, but we just need to know the length. So we know the length. So what you do, we have drawn this line already. You just draw an arc. So this is the B length basically. So that's, you see, this is the B length. So we know B length basically. The two intersection of the line and the arc define the two sets of solution. So wherever it's intersecting the vector A, the line of vector A over here and over here. So these are the two possible solutions for vector B. So we got two different options for this unknown. So two unknowns, we have two options. So one case, so one of the case when we have this one, so A, this is C, so this, sorry, this is B, this is A, this is C. So one is this one, yeah. So one is this answer where we have B, the magnitude is known. So the vector B would be like that. And how I know it is in this direction? Why is this pointing this direction? Because I'm doing C is equal to A plus B. So C should be head to tail method. So C is the addition of A and B. So that's why. And another case when A vector is such longer on this side, this A vector, then again, I'm following same way. C is equal to A plus B. So I just need to draw the vector B in such way I end up having C through head to tail method. So you see that's why this arrow is downward. So A plus B should be equal to C. So that what the so if let's say in case 2, as we had two unknowns, for such case we will have two solutions basically, right? So there are two different options. So you see in these options, the value or the direction of A or the magnitude of A. So it looks like this is A is small, this A is larger. So that's why we got two different numbers. I'm just making up number. Let's say this is 1 centimeter. So this is like a 4 centimeter. So when A is 1 centimeter, the B magnitude is like that. And if you have a source centimeter, but B magnitude is also like that basically. All right. Okay, so then we move on to the next case. Yeah, so you will get a little bit more idea what we are talking about. So in case 3, the two unknowns are two magnitudes A and B. So now this is the third case where you need to use figure 2.12 and equation 2.18. So what we have, A and B, both magnitudes. So both magnitudes are unknown. A and B both are unknown. So C is fully defined, vector A direction known, vector B direction known. So the solution illustrated in figure 2.12 is obtained as follows. Choose a convenient scale factor and draw vector C. So we know direction and magnitude for vector C, right? So we already know that one. So you draw that one. Construct a line through the origin of C parallel to A. So A vector, we know its magnitude. So that's why, sorry, the direction. So we just know this small to show direction. And for B as well, we know. So what you need to do, construct a line through origin of C parallel to A. So this A vector, you just draw a line indefinitely, like longer line like that. And then what you do, construct another line through the terminus of C parallel to B. So from terminus of B, so the end of B, you draw a parallel line like that. So you go like that basically, right? So parallel line to B. So this line and this line is a parallel. So which is of course the B basically. So where they are intersecting, that's the point. So the intersection of these two lines define both magnitudes A and B. So where they intersect, so you already know this is the magnitude. So you just measure this length and you measure this length, which is for vector B. So this length is vector B, this is that for vector B, and this one is for A. Yeah. So depending upon the situation, both can be, which may be either positive or negative. Why? Because in the end, the arrows will define, so the direction will be defined based on A and B. Yeah. So because sum is equal to A plus B, so the vector this one need to be drawn in such way from head to tail. And also we know the direction, so this case direction was known, so that's fine. So arrow is For A, arrow is downward. For C is arrow upward. So for A, arrow is downward because we know direction. For B, we have direction going upward this side. So this has one solution only. So it doesn't have two solution. Okay. Now we have the last case, which is case 4. So finally, in case 4, the two unknowns are direction of two vectors. So A and B, both directions are unknown. The vector equation, yeah. So this is the final case, and we are using equation figure 2.13 and equation 2.19. So that's 2.19. So same equation where we got A and B, both magnitudes are known, but the directions are unknown, A and B. So the solution is illustrated in figure 2.13. So how you obtain it? So what is it? Choose a convenient scale factor and draw vector C. So C is fully defined. Same way you start with C. So you have chosen a scale and direction as well. You draw C. Construct a circular arc of radius A centered at the origin of C. So you draw a circle. So you draw an arc with radius A. So we know the magnitude, which means we know the radius of A. So you draw an arc. So for example, this is vector C. By placing here your compass, you draw with the equal length of A, you draw this arc. You draw this arc. So that's the arc with radius A because we know the magnitude of A, and the A has to start with the origin of C. Now construct a circular arc of radius B centered at the terminus of C. So now the next is you place your compass over here. Let me make a different color. Let's do this one. Yeah, so now at the terminus of C, so at this point, and you draw another arc because we know the magnitude. So you draw this arc which has a magnitude B starting from here to end here, right? And now wherever both intersect those arcs, which is arc for A and arc for B, so they are intersecting at two different locations as expected. So that's the intersection point. So if this is first intersection, so then you draw, so this is C. So we know the magnitude. So direction you can indicate if this A is going upward, so the B would be in this way. So A is upward, so B will be in this direction that way. So if let's say A is downward this way, so B would be down. So you see, if there are two unknowns, angles unknown, we have two solutions for such case. That's why we have two solutions. And if let's say we got two magnitudes unknown, that straight away you just have one solution. If one angle and one vector, one vector direction and one magnitude is unknown, then you also have two different solutions basically. And in the first case, it was just one solution. So we can find out C is magnitude and as well as direction. So that was the simplest one. All right. So these set of equations or unknown are only, so this was defined. Yeah, sorry. So this one defined basically. So these are four possible unknown could happen during a planar vector equations. So planar mechanism, which we are discussing only in this module. All right, uh, so these are possible scenarios and possible solutions. And if we continue, yeah, so this is one of the example now. Slider crack linkage. We want to do is posture analysis. So slider crank linkage, consider the slider crank linkage as shown in figure 2.14a. So that's 2.14a. So given the position of link 4, so link 4 position is determined, is already known. The problem is to determine the posture of link 2 and link 3. So we want to find out the posture of link 3 and link 2 basically. That's unknown. So we will practice the knowledge we just got from different possible scenarios, and we will employ that knowledge over here to find out the posture for link 2 and link 3. So replace the link center lines, the first step. So replace the link center lines with vector RA. So for the crank, so this is the crank. So replace this with RA vector. RB for the slider. So RB is for the slider. And RBA for the connecting rod. So RBA is this vector, which is for the connecting rod. With a known location of slider, that is a distance RB. So we know this one, this particular distance. So we know this RB, the posture, we know the location. So so this RB vector is fully defined. That is the distance RB, and the angle theta 2 and theta 3 are unknown. So theta 2, which is this one, this is the one which will define what is the posture of this mechanism. So that's why theta 2 is unknown, and theta 3 is unknown as well. So theta 3 is basically the angle made from the positive axis. So in this book we are following the process where the angle is always measured from the positive x-axis. So if this is the one which is the vector which is going that way, so we need to see from the positive x-axis what angle is making. So that's theta 3. That's why it's a long way like that basically. So if you look at the one, this says that loop closure equation for the linkages is. So we use this one method, so which is basically RA plus RBA. So RA plus RBA is equal minus RB is equal to 0. Either you can write this way or you can write very simple way like that. What is this basically? So from this one is easy to understand. So RB, which is this one, is if you do head to tail method. So this is addition of RA and RBA, right? So RB is equal to RA plus RB, and the one he is using term loop closure equation actually, that is to do like that. So RA, which is making a one loop. So RA is in this direction, RBA is in this direction, RB if it is in this direction, then it should be positive. Yeah. So because it's opposite, so it's not making a loop. So that's why it's a negative basically. Yeah. So this is a little bit easier way if you try to understand. So loop closure means all vectors are in such way they are making a loop, right? So you can bring this one over there, and then you have RA plus RBA. where I symbol, so we are is just using another terminology, where I symbol, which is over here, for the direction of vector RB denotes the location of the slider is the given input. So because of the given input, that's why this symbol is being determined as a I basically for the given input of the slider. Because you know why we are saying so, the slider moves in this direction or in this direction. So if that's the input, will define how much angle of this vector would be basically. All right, so that's the possible scenario here. So we use the combination. Yeah, so I think one of the slide is missing. So the process is basically, so this is the case which is basically in line, which is in line with the case where you have two magnitudes unknown. So I will go back. Two magnitudes are unknown. So A and B magnitude is unknown. So this equation, so this equation 2.1. So equation 2. Yeah, so case 3, sorry, so this one. So where you have figure 2.12 and equation 2.18. So we got two magnitudes, sorry, two angles are unknown, right? So we got the angles are unknown. So that's what we are dealing with basically. So that's why if you look back, yeah, so sorry, so this is case 4 basically. So case 4 is theta A and theta B. So two angles are unknown, right? So that's the possible. So what you do, basically you know the length. So we know the length for RB. What you do for this slider position, you just use compass to draw two different positions basically. Yeah, so how you do that, you know that, so the two directions would be, so one is RA, you place the compass over here and you draw the direction. So you draw this arc basically. So that's the arc with RA. So so that's why you see this is RA radius. So this is RA radius, right? So you draw this arc, and then you got another arc which is basically from this from with the length of RBA. So you put your compass here. We know this length RBA. We know the length, and you just draw another arc. You see, this is a bigger arc which is drawn by putting your compass over here and all the way over here, right? So wherever those intersect, that's two different options actually. So what does this mean actually? So when slider at this position, your crank could be at this position or else at this position. If you look back, you would understand, because this one is moving, this crank is moving. So this crank is downward. So this slider can also be at the same position if the crank is up here or crank is down there. So that's why we got two solutions basically. So again, let me explain again. So this was the case where we had two directions unknown, means two angles are unknown. So theta 2, theta 3 unknown, all other lengths are known basically. So we have to do the case 4 where both angles are unknown. So how we have done that one, when you knew the direction, sorry, when you know the magnitude, vector A magnitude, vector B, so you place your compass here, you draw this arc, you place your compass here, you draw this arc, wherever they are intersecting, these are the two possible solutions.
right? So same goes over here. You place your, because this, the crank can make this angular movement, it can draw this circle. So RA is making this circle, RB is making, so RBA, the connecting rod, because it is also making a turning pair, so this can move up and down, so this can move up and down. So that's why you draw another arc, which is this one, right? Yeah, so once we have the intersection, so these are possible solutions. So now you can literally determine the angle. So you can measure the angle actually. If this is at this location, you can measure what is this angle. So this theta 3, you can find out this angle. And when it's at this location, so you can work out what is this angle. So that's the crank angle, so theta 2. So we got two different options. So this is theta 2, right? Theta 2, what is theta 2? From the x-axis to the crank. So this is theta 2 when it's at position A, when it is in position prime. So this is theta 2 prime. Yeah, so this is one of the angle basically. Theta 2, there are two different possible solutions for theta 2. Then another angle we were interested in, basically theta 3, which is for the connecting rod. So connecting rod, if it's at position A, is making angle theta 3, and when it is at angle position A prime, so from the, again from positive x-axis, we have theta 3. So there are two possible solutions. So you have got theta 2 and theta 2 prime, and respective theta 3 and theta 3 prime, right? Okay. Now we are doing similar analysis for 4-bar linkage. Uh, so, so this was very interesting example where we can use such method to find out if the given slider position, we know what are the possible locations or the posture the other links can have. So that's why this is a kind of like interesting analysis for the mechanisms. Now the next example, little bit extra information. So as you consider the 4-bar linkage shown in figure, given the posture link of link 2, so that's the link 2, that's the link 2. The problem is to define the posture of link 3 and link 4, right? So the link 2 is this one. So we know, so first of all, in this mechanism, this kind of mechanism, we know exactly the locations, sorry, the magnitudes, the lengths, the angles are unknown. When we say we want to do posture analysis, we are mostly doing the angles actually, which direction the mechanism would be. So we got this link 2, which is basically the we know the angle theta 2, and we know the length, and the unknowns are, so you see, you remember, because it's all rigid, so this whole is link 3, so this whole is link 3. The unknown is this link, we don't know what's its position, what the different angles are. And link 4, so this one we also don't know what is this direction, theta 4. So theta 3, theta 4 we would be interested in determining. So same way what you do, so replace the link center lines with the vector. So important thing is you need to do the center lines, because that's important. So for example, RA represents this one, link 2, RA, that's a vector, which is called as a crank. RBA for the connecting rod. So RBA basically is this one, which is the connecting rod. So this is the connecting rod, right? So that's the connecting rod. That's this is the representing connecting rod, RBA. For the output link, and RBC for the output link. So this is the output. So this is called as output. So this is RBC, right? So this theta 4 is unknown. And RC for the frame. So that's the frame. So this is a frame. You might remember this we used to do when the fixed link. So we consider it as a RC as a one of the frame. With a known posture of link 2, that is the angle theta 2. So the known position of angle 2, so we got this one, angle 2, theta 2 is known. The angle theta 3 and theta 4 is unknown. So theta 4 and this little angle theta 3, which was over here. So basically this was shown here. So from the central line, so this is the central line for the mechanism, and then we have theta 3 basically. So that's the theta 3. This is unknown. So these two are unknown. The loop closure equation of the linkages. Same way we can write the loop closure equation. So crank, so that's the origin. So crank vector A is that way, BA is that way. So RA plus RBA and RBC, which was supposed to be this way, because yeah, if it's that way, then it's positive because it's loop closure. So let me make it like that. So this vector this way, this vector this way, this vector this way, this vector. So it's making full loop. So this kind of assembly would be all vectors positive. But now this RBC is outward that way from the fixed point C. So it's outward. So that's why it is negative. So minus RBC minus RC. So RC is also minus basically because this is in that direction as well. Or else you can write, yeah, positive negative each side. So RA, RBA on one side and RC and RBC on one side. So what is unknown in this one? So RA, that's the input. So that's why it's written as a I. So, but we know its direction is magnitude. So this is well defined. RBA, because it is angle theta 3 is this one. So this is unknown. So magnitude we know, the length we know. RC, which is basically the frame, this length and vector, so is fully defined. RBC, same way, the angle C, theta 4, this is RBC. So we know its length, but we don't know its direction. So theta 4 is unknown. So that's the equation we will use now. We will try to solve this equation. So again, where I symbol for the direction of vector RA denotes the orientation of the crank in a given input. So that's the input. So that's why it's defined. Also, the position of coupler point P is given by the position difference equation. Yeah. So now this coupler position. What is coupler here? Coupler is basically this position, this point. This is another thing here, which is basically RA plus RPA basically. So just a second. So RA plus RPA. So when we say this P point, so RP is the vector, this one. Yeah. And RA is vector, this one. So which is already the input. So this is vector and this vector is same. And RPA, which is basically this one. So basically that's the way it is actually. So you can do the analysis like loop closure analysis, or else you can write like, because RP is the sum of RA and RPA basically. So that's the positions for point P of the coupler. Yeah. So this is for this particular point basically. Yeah. So this is like drawing different triangles like this, for starting from here with reference to this one, and then this angle, then this one. So these vectors are like that. So this from here, and this one from here basically. Note that this equation contains 3 unknowns. Yeah. So RP, both unknowns. RPA, one unknown. So within this equation we got 3 unknowns, but this can be reduced to 2 after equation B. So using this equation B, you can replace this equation and you can you can plug in as a 2 unknowns basically. How you do that? Solving by noting the constant angular relationship between RPA, between this RPA and RBA. So this RBA, because you know uh, this angle alpha is constant, it's not changing from this line to this line, so that's why he is defining theta 5, this whole angle, as a theta 5 instead of like alpha. So theta 3 plus alpha would be theta 5. So let me clear it. So what we are doing, because this angle, little angle, uh, this little angle is alpha to this link, and after that this angle is theta 3, right? So why not to add together? So theta 3 plus alpha and replace it with theta 5, and theta 5 is equal to theta 3 plus alpha, right? So where the constant angle alpha, so this angle alpha, which is BAP, so this BAP, alpha is the angle, that one. Therefore, the equation C reduces to, now this equation, you can reduce it to RP is equal to RA plus RPA. Now, the RPA, which is this angle, he's just writing its magnitude is known and its angle or orientation as a C, basically another variable. So instead of, so this one, which is like unknown, and this is can be replaced with the theta 5 is equal to theta 3 plus alpha, and we're writing as a C, basically, right? So determining as a and one of the parameter, basically. So where C is a symbol for the direction of RPA, denotes that this direction is known from the constrained equation, that is equation D. So the equation D, so this equation D, which shows that this angle is basically is known, right? If what does it mean? If you know theta 3, you already know theta 5, basically. So that's what it's trying to establish, and therefore it is not a third unknown. So that's why you don't consider it as a third unknown. So this is basically known. So that's why is writing this symbol C. We begin the graphic solution by combining the two equation terms in equation B, thus locating the position of point A and C as shown in figure 2.16, A and B. Yeah. So now what we have, so you combine both equation. So by combining the two unknown terms in equation B, so we are combining these two unknown equation B. So basically this one. How you doing that? You're bringing this RC over here and RB over here. Yeah. So you see RC. So basically RC minus RA. Yeah. So it's the other way around. RC minus RA, which is this one, right, is equal to RBA, this one, minus this term which you brought this one over here. So RBC, right? So within this one, you see there are two unknowns, RBA and so what we are trying to do, we begin the graphic solution by combining the two unknown terms in equation B, thus locating the position of point A. Point A is this one, and point C and C. So what we are doing, basically, we are finding RC minus RA by using this equation and replacing that vector with S. What is S? S, you know, this RA and RC, when you subtract it, this vector would be S. Yeah. So we know this vector, we can calculate this vector, basically, we can do this distance. So by using that one, we can further calculate what is angle theta 2. We'll see now. So we recognize this equation as case 4 in table 2.2. So this is particularly the case 4, right? What is case 4? Where two angles are unknown. I'll just go back. So in case 4 we had two unknowns, the angles are unknown basically. So we got yeah, so table 2, the solution procedure, that is two unknown orientations. Yeah, it is then used to locate point B. So now using that one we can locate what is where the point B would be basically. Yeah, so okay, note that two solutions are possible, which indicate that the 4-bar linkage can be assembled in two different postures. The two postures will be referred here as A, which is this position, as an open posture, and in figure 2.16a, and B, the cross posture shown in figure 2.16b. So this is the posture. So how actually you do that? So once we know the S basically, and we know the length RBC. Yeah, so this one is quite clear actually, because once we know the C, sorry, the S value, this length, yeah, so you know that where, so you draw basically, because you know from this one, from the directions, you can just find out the differences. So this one, yeah, so when you draw it basically you can find the angle, and you can measure the angle as well. So this theta 2. Yeah, and once theta 2 is known, you can work out the other angle as well. Of course, when you know this one, so you can find out, because this, for this length to this length is a constant, so you can work out theta 4 as well. So theta 3 and theta 2 and theta 4 were the main unknowns. Yeah, so now the RBA basically, the connecting rod, this one, so this is another position, because this one you place your like with the known length of RBA, what you do, you draw, because this is connecting rod, you draw a compass and you draw a arc, right? Because this can move, the connecting rod can move in this all this direction with the known and length of RBA, and you have, you draw an arc basically, right? And then this RBC, which is this length RBC, you place a compass here and you draw another, because this also make a circular, so this RBC can make a circular motion, so which is basically like the length is known, so it will intersect, so you draw another circle like that basically. So that's so wherever so it intersect here, so that's why we have this posture A. Another intersection point, which is this one, so this is another posture basically. So of course this is the position for RBA, so that's RBA, and we also have this one, so which is when this intersecting, because this is RBC, this is the one we draw the circle, so this is RBC. And then the angles are just like from positive x-axis, so from positive x-axis, this is the theta 4, that what, yeah, you have drawn here, and then you got the angle, yeah, so other angle we need theta 2, so theta 2 is that, so that's theta 2 is same, because we are just plotting from here. Theta 2 would not change, it's just the theta 3, oh sorry, theta 4, which is changing quite a lot, so this is theta 3 and this is theta, yeah, theta 4 basically. Yeah, and then of course other postures, other analysis would also change if, let's say, RBC is that way, because we know the angle alpha. If we know this side, so you draw with the known alpha angle, you can draw this one basically. Yeah, so that will give you the point P basically. Yeah. So yeah, so that's it, because you can find out. So because you have located B, you have located P point, and we located point B, and this one is not changing, so that's what we have here. So for the given angle theta 2, which was yeah, so with the known angle, so angle theta 2 was known, so this angle theta 2 is known, and theta 3 and theta 4 are unknown. Yeah, so theta 4 we have found there are two different options. Theta 4 is this one, and theta 4 is this one. So it could be this one, this link RBC could be at this position, or it could be at this position. So that's why we have two values for theta 4, and of course theta 3, which is now yeah, so this angle theta 3, which was from positive x-axis, theta 3 for RBA, when it's we are talking about RBA over here, so theta 3 from the positive x-axis will all the way over here, starting from here, because that's the RBA, so that's why we are over here basically. So that's theta 3. So two unknowns, and we found two different positions. So again, with the given angle theta 2 for this crank, the mechanism can have two possible orientations. One orientation, the way it is also shown, which is simple to understand. So this is the one position, and the other position is basically is this one, where you got theta 2. So but other links are at such position, they are intersecting over here. So we got theta 4 and theta 3 basically, right? So if you can list theta 3, theta 4, and with the constant theta 2 by plotting this one the way I have shown you, by drawing the arcs, the, starting from here, the arc basically making this one, and from here RBC of this one. So then you can easily find out theta 4 and theta 3. So these are the two major unknown, and of course then you can plot what is alpha and any other angle which has been involved. So RP, this was shown as a theta 6 over here, so you can show this one as a theta 6 over here, but all angles are shown from the positive x-axis basically. And theta 5, which was shown here like this one, this total angle, so you can show this one from the positive x-axis as well. Yeah, so that's it.